Hello and welcome to the new episode of the Network and Cisco Packet Tracer tutorial for beginners. Siawash is here, and today I want to talk about the STP or Spanning Tree Protocol. STP is a layer 2 mechanism to prevent the loop in your network and ensure that you have a loop-free network environment. Sometimes in your networks, because of redundancy, the loop will occur. Let's take a look at this scenario here. Okay, we got three different switches, 2 PC and 1 server. They want to communicate to each other. Let's say PC number 1 try to find this server. So to do that, it will send one broadcast from this switch. This switch will send out the broadcast from this way and this way. When the switch number 0 receive the broadcast, it will send out to all other ports except the receiving one, which means this way and this way. At the same time, this switch also received the broadcast from switch 2, and it will send it from this way and this way. But don't forget, this switch also received another broadcast from the switch number 0, which will send from here and here. It also happened on a switch 2. When it receives any broadcast from this side, it will send it back here, and when at the same time this switch receives the broadcast, it will send it back here, and this switch continue to sending all broadcasts to all the way, and it will make a big loop and broadcast storm in our network, which bring down our networks. So how the spanning tree can help us to prevent the loop in our networks. So before we going to the process, let's show command here. On the switch number 0, I enable the switch and use the show spanning tree and press enter. As you can see here, there are some information about the spanning tree on this switch. We have a root ID, we have a bridge ID, some numbers like priority and address here also, and hello time, some information about our interfaces. Let's try with other switch here. Switch number 1 is a good option, and enable show span, and here also we got almost a similar information, root ID, bridge ID, other information. As you can see, the root ID is priority and address is here. And let's finally go back to the switch number 2 and enable and show spanning tree. And here we check root ID and bridge ID, but there is one difference. This bridge is the root, and why this switch is elected as a root. So STP will following these steps to find the root bridge and prevent the loop in our networks. First of all, these switches find the root bridge, so elect the root bridge is the first step. Then each switch tries to find the best path to the root bridge, so select the best path to root bridge. And finally, block unnecessary ports. Yeah, okay. These are the steps to select the spanning tree in our networks. But how this switch select the root bridge? The root bridge is based on the router ID, and router ID is also contained with the number as a priority plus the MAC address. So I write it down, root ID or bridge ID, which is better we call it bridge ID, because when it's elected as a root bridge, it will be set as a root ID. So bridge ID will be the number 32768 plus the MAC address. But actually the number 3268, okay, 768 is plus VLAN ID and MAC address. As you can see here, let me zoom it and show you. And the bridge ID is a 32769, which is 768 plus 1, which is the VLAN 1 in our networks. So, and the MAC address, as you can see, these switches have a MAC address. In spanning tree protocol, if the bridge ID are the same, the MAC address will help us to find the root bridge. And in spanning tree words is always the lower is better. Let's take a look at the MAC address of each switches in this network. To do that, we have several ways. One of the ways is using the show spanning tree. As you can see, we can find the MAC address of our switch as well as our root bridge, and another command which will help you is a show version. And here we are. Yep, you can see the MAC address of the Ethernet switch here, and this is 5102 is almost equivalent to here our bridge ID 5102. I don't read the entire MAC address, it's too long. Okay, so let me zoom back here and on a switch 2. Okay, show a spanning tree, and this bridge is root bridge, and let's write down these numbers: 32769, 0001, 6311, and 055E. We need to compare the MAC address of each of them. I'll leave it and try to open them side by side. And okay, where is the other one? Yeah, okay, this is switch 1. This is a switch number 2. Let me do the one show span, and we can compare them side by side if possible. And finally, where is the switch number 2? It's here. Okay, I hope I can zoom and show it to you. Okay, let's zoom it. Okay, here we are, the switch number 0 and switch number 1. The priority are the same, 32769 here and here, but look at this. Sorry, you shouldn't look this. Look at the bridge ID here. Actually, by the way, the priority are almost the same. Okay, the address is 0005 and 0007. Which one is lower? Obviously this one. Okay, so for that reason, but take a look at the root ID MAC address 0001, which is lower than both of these two MAC address. And if you take a look at this, let me zoom and go to the switch number 2. Okay, you can see here this bridge is root, and the bridge ID and the root ID will be the same, 32769, and the MAC address 0001.631111. And here in other switch, we can see our MAC address is higher than our root bridge. So the MAC address and the bridge ID can break the tie as I show you. So we can learn here this switch became the root. Then each of these switches try to find the best path to the root. Let's take a look at this table. Okay, these are some information for you, and it shows that the data rate and spanning tree cost for each link. If we have a 10 megabit per second link, the spanning tree cost will be 100. If we have 100 meg links, which is a normal Cat5e and Cat6, nowadays it's a spanning tree cost will be 19, and finally for the 1 gig like the Cat6, the cost will be 4, and etc. So in the spanning tree, as I mentioned, lower is better. In this scenario, each of our links between these switches are the normal 100 megabit per second link, so the cost will be 19. Here we are, another 19 here. I just write down for you. This helps you for better looking at this scenario. Okay, we have 3 links here, each cost 19, and this is our root bridge. As we can see, the bridge ID of this switch is elected as a lower one and as a root ID of this topology, so we call it root bridge. And here we are. So switch number 0, try to find the lowest cost to the root bridge, which is this link. So switch number 1 also try to find the best path to the root bridge, which is this link with the cost of 19. And finally, between these two switches, we will see one of the side of our links is orange or black. You may ask why it's like that. You may guess this one. Just back about the bridge ID again. In a spanning tree, lower is better, so we can compare the bridge ID of the switch 1 and 0. Let's take a look at this. Switch number 0, this switch, and switch number 1. Okay, here we go. Switch number 0, side by side. And let's zoom it and see why one of the links are blocked and the other one is not. Okay, let's take a look at here the bridge ID here. On this switch, the MAC address is lower, so the switch number 0 is still on a forwarding mode. As you can see, the information about the interfaces. FA0/2 is a root bridge with the cost of 19. The others, two other path ports will be designated and still forwarding. But in this switch, as you can see, on the switch number 1, one of the ports is a root bridge, which is these links here, and the other one is as a FA01 is blocked, and because of the higher MAC address and total bridge ID. And this is how the spanning tree protocol actually works. The process is sometimes take time, it depends on your scenario. And let's see about how it really works and how you can configuration the spanning tree protocol, because the bridge ID is based on the priority and the MAC address. Sometimes the root bridge is not the exact root bridge the network administrator wants. For example, in this scenario, as we can see, this access level switch became a root bridge, which is not very good idea, because if this PC want to communicate with this server, should go to this switch and then reach to the switch number 0 and reach to our server. So for better performance, it is better we select the switch 0 as a root bridge of this topology. And usually it's better the root bridge is be in our center of your network or as the core or a core level switch. Okay, let's see how we can make the switch 0 as our root bridge. You may guess that we can play with the bridge ID of this switch to make it lower and make it as our root bridge. So we go to the global config mode here and we use the spanning tree and question mark as usual. As you can see here, we can set the mode, the port path, which I explain in the further videos, and the VLAN. So go to spanning tree VLAN. In this scenario, we got one VLAN only, and question mark again. I can change the priority number, set the bridge priority for the spanning tree, or I can use the keyword root. I use the root and question mark. In case in your core level of your network you got two core switch, you can make them as a primary and secondary root, which one of them goes down, the other one can take a lead of the spanning tree. And finally, press enter. I show you spanning tree, VLAN number, root primary, and press enter. So you can see these topology start to changing. The switch number 2 is no more our root bridge. Let's move this root bridge here and waiting to the spanning tree process is finished. Okay, let me Control Z here. and show span here, see is changes happening or not. Yes, as you can see here, what we got, this bridge is our root, the root ID here, and the command we enter is automatically bring down the priority level to the lower than other priority. Even our MAC address is higher than the switch number 2, which you remember 0001. Let's take a look at other switches here. Okay, I'll go to enable, show span, and yes, as you can see, even the MAC address of this switch is lower, but because of the priority, our root ID of the root bridge is lower than our standard priority of our switch. Okay, so now this switch will be our center of our networks. Let's do some exercise on this. I go to the PC number 1. Okay, let's go to the command prompt and do the ping in packet tracer. It's a bit different. You should try ping -t and 192.168, and okay, let's ping the server and see. Okay, is it pinging? Did I set the IP address? Let me check. Go here. Oh no, I didn't set any IP address. 192.168. Let's make it fast. 11/24. Okay, PC number 2. It will be 192.168.0.10. Okay, class C/24, and finally our server. I mentioned 192.168.0.1, 192.168.0.1, and class C. No need the default gateway or DNS setting yet. Let's back to the PC and the command prompt, up arrow, and press enter. Now you can see we can continuously ping from this PC to go to the server. Let's do some exercise. I want to shut down this port and see what's happening. So to do that, I go to the switch number 2. Let's bring the ping here and see that. Okay, FA01 if I'm not mistaken. Yeah, this is a root FA0. I will shut down the root port on this switch. Go to the interface configuration mode, config T, then interface FA0/1, and using the shut, and you take a look at this ping is goes down, and I use shut. Okay, it goes down, and you can see this thing became red, and we received some request timeout. The spanning tree protocol automatically try to move and select the path to the root bridge from the other switch, but it's used still. You can see the request timeout. Wait for here. This switch, this link goes down. Review. We expect that our packets goes from the switch 2, then switch 1, then switch 0, and finally the server. Okay, how many ping we lost? 1, 2, 3, 4, 5, 6, around 10 to 15 seconds. This takes times. I don't go to detail, but for spanning tree protocol, each switch sends the BPDU on each 2 seconds to find the root bridge. Okay, then you see we get back our pings here. And 1, 2, 3. Let me pause this and take a look. 1, 2, 3, 4, 5, 6, 7, 8, 9. Around 10 pings we lose, which takes around 15 to 20 seconds. And now our packet goes from here. Even our link goes down or something happened, the switch can find the best path to the root. By the way, as you can see, for the modern network, especially with voice over IP, these number of the loose pings are not very efficient. In the next video, we will see how the rapid spanning tree protocol can help us to reduce even this convergence time. Okay, thank you very much for watching this video. I hope this is useful for your learning and your real networks. Next video we will talk more about the other mode of the spanning tree protocol. Thank you for watching again, and see you in the next video very soon. Bye for now.